looking at redox, and when you look at redox reactions, we have two processes going on. One of those processes is oxidation, which is a loss of electrons, and that just means that if we have a loss of electrons, the charge is going to increase. So we can look at something like, let's give an example here. Let's suppose we have, let's say, charge increases. Let's say we have some iron, Fe, and it undergoes a process that causes it to make Fe3+. Okay. In this situation, this is just naturally occurring iron metal over here. What would its charge be? You know. 0. Good. So we've got iron with a charge of 0. It becomes iron with a charge of 3. So if we've got iron with a charge of 3, that means we also have 3 electrons being given off. So 3 electrons are going to be a product of this reaction. Now these electrons are going to go somewhere, but if we're just looking at the iron is going from 0 to positive 3. That's an increase in charge, which means that we have an oxidation going on. So this would be an example of an equation that could be an oxidation process. Now we could also have something like this. Say we have sulfur with a -2, and it becomes sulfur 0, elemental sulfur. That's still an increase in charge, and if that happens, we would have 2 electrons given off. So we don't have to start with 0, we can start with something like -2. And another example that's maybe a little bit different, let's suppose we had iron with a +2, which is a possibility, and it undergoes a process that causes it to become iron with a +3. Then we would have 1 electron given off. But in each of these situations, we have different starting points, but what they all have in common is that the charge is going to increase. Okay, we also have reduction is another possible process. In fact, when we look at this, the red is reduction, the ox is oxidation. So reduction is a gain of electrons, and the charge is going to decrease. So to give some examples of that, we could have something like sulfur 0 becoming sulfur -2. Okay, now in this situation, where would the electrons be? On the 0 side. So we've got sulfur with a 0, we add 2 electrons to it, and we end up with sulfur with a -2. So as we go from 0 to -2, that is a reduction in charge. So the word reduction means in charge. Okay, and likewise, you could have really the reverse of this reaction. You could have iron 3, and you gain an electron and you become iron 2. So that would also be a reduction in charge. So we can, again, start in multiple places. We don't have to have a charge of 0 to begin with or to end with, as long as the charge is going down. Now, when we have charges created, like here we've had some electrons produced. When we have electrons produced, or we have negative charges produced, there has to be an offsetting positive charge produced somewhere else. That isn't one of our conservation laws. We've covered law of conservation of mass. We've probably mentioned law of conservation of energy a few times, but this is the law of conservation of electrical charge. Electrical charge is neither created nor destroyed. What that means in terms of oxidation reduction is that, first of all, if a positive charge develops, we have to have the offsetting negative charge, and vice versa. But what it really means is that whenever we have oxidation and reduction, they have to happen simultaneously. You can't have one without the other. So whenever a charge increases somewhere in another location, a charge has to decrease, okay, by the same amount. Overall, the universe seems to be electrically neutral. So if we have a positive created, there has to be a negative to neutralize it. All right, so let's take a look at some example problems. We've got zinc metal reacting with copper 2 sulfate. Okay. We're going to do several things to this, and you can see the list on your outline. We're going to write the equation. We're going to assign oxidation numbers and charges. We're going to identify the species that go through a change in oxidation state. we're going to identify something called the oxidizing agent and the reducing agent. And we're also going to write half reactions for the processes. All right, so let's go back, and I'm going to start by writing the equation down here toward the bottom. And you can help with this. First of all, we've got zinc reacting with copper 2 sulfate. So let me erase that. I've already started wrong. Not really wrong, just not in the order of the problem. The order doesn't matter, though. So we've got zinc plus CuSO4. Okay, this is zinc metal, so we would call that solid. And it's reacting with a copper 2 sulfate solution, so we would make that aqueous. Now, what kind of reaction is this? Okay. No. This is single replacement. Keep in mind that the classification of redox, that process doesn't mean that it's not either single, double replacement, synthesis, decomposition, or combustion, or redox. Redox overlaps with all of these. So some of all of those are potentially redox, others are not. We'll talk about that later in this lesson. So what are our products going to be? And that does require zinc to be above copper in the activity series. It is. And plus what? It is copper. So copper metal is produced. That would be a solid, and that's aqueous again. And I believe we're already balanced, so there are no, all the coefficients are 1. Yes. Okay, so we've written the equation. Next, we want to assign oxidation numbers and charges to every part of this equation. Okay, so let's begin with zinc. This is zinc metal, which means pure zinc. Pure elements always have an oxidation state of 0. Copper 2 sulfate, what's the charge of the copper? It's copper 2 sulfate. Copper 2 is copper 2 because its charge is 2. Okay, so that's positive 2. I'm going to do sulfate separately, so I'll come back to that. Zinc over here, zinc has a positive 2 charge, which is its only oxidation state, and copper metal is at 0. Remember, pure elements, always 0. Okay, so for sulfur and oxygen, we can actually go ahead and assign the oxygen. As usual, it's a negative 2. But if we're looking at sulfate, it overall has a negative 2 oxidation state. So if the oxygen is negative 2, then what's the charge of the sulfur? So what equation will we write from this set of numbers? We got 1x, or x, minus 4 negative 2's, minus 8, equals negative 2. So add the 8 to both sides. So x equals 6. Okay? So this is sulfur 6. Go ahead. X, 1x, 4 negative 2's, negative 8, equals charge of sulfate, negative 2. And then I just add the 8 to both sides, and positive 8 and negative 2 is 6. All right, now let's look for things that have changed. What has experienced a change in oxidation state from the left side of the equation to the right? Okay, so that's one of them. Exactly. Okay. Now, so at this end we've got positive 2. At this end we've got 0 for the copper. Is that an oxidation or a reduction? That is reduction. That's a decrease in charge. So that's a reduction. So the other one has to be an oxidation because they have to occur together. But make sure you see why. We've got a 0 here on the zinc, On the other side, it's a positive 2. That's an increase in charge, so that means oxidation. Okay. So we have identified the species that have undergone a change in oxidation state. Now let's also talk about, this is something that's not up here, but let's look at how many electrons were transferred. We have 1 zinc on both sides. That zinc goes from a 0 to a positive 2. So how many electrons were transferred? We're going from 0 here to positive 2 there. So that means a transfer of a certain number of electrons. It has to be 2. And are those 2 electrons gained or lost? 2 electrons lost from the zinc. On the reduction, we've gone from a positive 2 to a 0. That's also 2 electrons. But since we're going from a positive 2 to a 0, we're decreasing in charge, so that's 2 electrons gained. All right, let's talk about the oxidizing agent. These are some, I think they're confusing terms, always have, but it's sort of one of those things that the history gives us these terms, so that's what we have to deal with. The key is, and what the definition here is that the word agent has a definite meaning here. Agent means something that causes something to happen. So an oxidizing agent causes oxidation. And likewise, a reducing agent causes reduction. So let's look first at zinc. Okay? Zinc is oxidized. What caused zinc to oxidize? It did lose 2 electrons, but where did they go? Right. So they're lost from the species that was oxidized, and they're gained by the species that is reduced. So as zinc becomes oxidized, the reason it's oxidized is because it's interacting with copper. So copper technically is the agent, that copper 2 specifically is the agent that caused zinc to become oxidized. What happened to the agent? What did copper do? It reduced. So it becomes reduced. So if you look at it this way, if you cause something to become oxidized, you're going to become reduced in the process because you're taking electrons away from it, which causes its charge to go up. And likewise, the flip side of that, here we have copper that was reduced. What caused it to become reduced? Zinc gave it some electrons. So it causes reduction. Zinc causes reduction. But what happened to zinc? Becomes oxidized. For the zinc, it started with 0, but it goes to positive 2, so it gave some electrons away, reducing the copper from 2 to 0. Now, what about the sulfate? Any change there? Sulfate didn't go through any change at all. There's no change in oxidation state. And whenever you have something in an equation that is present on both sides, and it's unchanged, what's its real purpose? It does nothing chemically. It doesn't go through a chemical change at all. What its purpose is this is a soluble substance. If we have copper with sulfate, the sulfate carries the copper into solution. So it allows the copper to go in. It also allows the zinc to stay in solution. So what we call those, let's say you go to a football game and instead of participating in the actual football, you're not on the field, you're in the stands, what do we call those people in the stands? The what? Bystanders. That actually works. What'd you say? Fans, that's true. Not the answer. Bystander is actually a better answer. There's what? Audience works. Teacher. No, a little too specific. Giving you a hint. Spectators. A spectator is something that's sitting back and watching, but not actually being involved in the process. So anytime we have, and you're going to see this in more detail in our next type of equation after this, anytime you have a species that is there, but it's not actually doing anything, we call that a spectator. So sulfate is actually acting as a spectator in this situation, not really involved. So our next process is to write something called a half reaction. And a half reaction is going to, how many halves make a whole?
Two.
2 halves make a whole. So we're going to have 2 half reactions to make a whole reaction. I'm going to write these up here because I'm out of room down below. So what we would do, we have 2 processes and 2 halves. So those 2 processes are the oxidation half reaction and the reduction half reaction. Okay, so again, what goes through oxidation? Zinc. So we start with Zn0 and we end with Zn2+. Okay, and where are our electrons? Oxidation, you're giving off electrons, so they would be product. Okay. That is the oxidation half reaction. The reduction half reaction is going to be copper yields Cu0, so we're writing the species in its original form and then in its reduced form. And we're going to add 2 electrons. Okay. Now, another little interesting feature of this, besides having half reactions, we can add half reactions together. So we're going to do that. It's very simple to do, no complex math rules or anything like that. You see where the yield arrow is, so you write the things that show up on the left side and then on the right side. So you've got Zn0 plus Cu2+ plus 2 electrons yields Zn2+ plus Cu0 plus 2 electrons. Now, we have some things that are the same on both sides. What are those things? The 2 electrons. So we can actually cancel the 2 electrons from the final reaction, and we end up with this situation. I'm going to do it this way so it clears it up and I'm out of space to rewrite it. The overall reaction can be described by this last equation. Zinc metal in the presence of copper 2 ion becomes zinc ion with a positive 2 and copper metal. So what this is showing is very specifically what's happening in this reaction. The sulfate's not included because it's a spectator, and we reduce it down to its most bare bones. This is actually called a net ionic equation, although we're not truly doing net ionic equations yet. So in this reaction, does it matter that copper was with sulfate? Not at all. This copper could have been with any ion that let it go in solution. So this same reaction would happen if this was copper 2 chloride or copper 2 nitrate or any copper compound that will go into water and make a solution in the presence of zinc metal would cause this reaction to happen. because the anion's not involved.